This video on rational functions is going to answer the essential question, how do you solve rational inequalities? We've seen before solving rational equations, and now we're going to replace the equal sign with a greater than or less than, greater than or equal to or less than or equal to sign. And what you'll notice is that for rational inequalities, we are going to include, along with the zeros, the values that make the inequality undefined as well, and include them in a sign chart. Now we're used to solving polynomial functions, polynomial inequalities with a sign chart, and now we're going to solve rational inequalities with a sign chart. So let's start with the values that go on our sign chart. So with polynomials, we always started with the zeros, and we start that same place for rational expressions, and the zeros come from the numerator set equal to 0. So in our case here, we've got x minus 5 in the numerator, set that equal to 0, and x equals 5 is the 0 of this rational expression. Okay, and this sort of bubble above the problem tells us that not only are we interested in the zeros, but we're also interested in where this expression is undefined as a potential location for where the sign changes. And what makes this rational expression undefined is the denominator equal to 0. And so that's our x plus 1 equal to 0, so x equals negative 1. So these two values, 5 and negative 1, are both now going to show up on our sign chart. Here's x equals negative 1, and here's x equals 5. And those values, one of them is a 0 and one of them is an undefined value in our original expression, are going to be potential locations for where the graph changes from being above the x-axis to being below the x-axis. Potential locations for where this expression is going to change from being positive to negative. Now what's going to be important in our final answer is making the distinction between x equaling 5 being a 0, and I'm going to label it with a z above that to remind myself that that's a 0 of the expression, and x equaling negative 1 being a value that makes the expression undefined. So I'm going to put a u above that. Those labels are going to remind me in our final answer, it's going to remind us whether we want to include the negative 1 or the 5 with our final answer. And you might already suspect that since x equals negative 1 is what makes the expression undefined, we're not going to include that negative 1 in any of our answers. So let's check the signs. We can do the signs a few different ways. We can simply pick a value that's less than negative 1, let's say negative 2, plug it into the rational expression, and then figure out if the expression is positive, figure out if it's negative. If we do negative 2, in the top we get a negative, in the bottom we get a negative, and a negative divided by a negative is positive. Okay, the same approach if we look at x equals 0 and plug it in the top, in the bottom we get a negative divided by a positive, that gives us a negative interval. And then something greater than 5, let's say 6, is going to get us a positive divided by a positive, and that gives us a positive interval. You can also use the multiplicity of the zeros and the undefined values. This x equals 5 has a multiplicity of 1, and this x equals negative 1 has a multiplicity of 1. Multiplicity equals 1. That tells us that the odd multiplicity is the signs are gonna change on either side of the undefined value and on the 0. What we don't know is the end behavior. We might analyze the end behavior to see what the signs of the outside intervals are. If you remember, for end behavior we generalize our expression x minus 5 divided by x plus 1 to x over x that reduces to 1, and that tells me that my end behavior actually in both directions, towards positive and negative infinity, of this x minus 5 over x plus 1 equals 1. And 1 is positive. This is a positive 1. So that tells me that the end behavior intervals are both going to be positive. So that's how we determine the signs on the sign chart. Now the final answer, if we go back to the inequality, the final answer to this inequality is going to be the portion of this sign chart that makes the expression greater than or equal to 0. So here's an interval that makes the expression greater than 0. Here's an interval that makes the expression greater than 0. And only one of these numbers, only the x equals 5, actually makes the expression equal to 0. We don't want to include negative 1. That makes the expression undefined. So our final answer are going to be the union of the interval from negative infinity to negative 1 without including negative 1, and the interval from 5 to infinity where we include 5. And that's the final answer based on the sign chart that we came up with. Let's look at another example. We'll follow the same exact approach. We'll first start out finding the zeros of this expression, and we'll take a look at the numerator, 2x plus 1 equal to 0, and we'll solve for x equals negative 1/2. We'll look at where this expression is undefined. That's the denominator, x squared plus 2x minus 3 equal to 0. Since this is quadratic, we can solve it using a number of different approaches. So let's factor, so x plus 3 and x minus 1 equals 0. That gives us two values that make this expression undefined, and that's going to be x equals negative 3 and x equals positive 1. So our sign chart here has three values on it. We've got negative 3, and we want to be careful that we're putting these in the correct order. Negative 1/2, and then positive 1. And remember, we want to label each of these correctly so that in our final answer we're not including the undefined values. We're only including the values that make the function 0. So we put a u above the undefined values that make the function or the expression undefined. We put a z above the x value that makes the expression equal to 0. And now we go about finding the signs of the sign chart. We saw last example the end behavior got us the signs on the outside, but in this case our expression generalizes to 2x over x squared, which then reduces to 2 over x, which gives us end behavior in both directions, both towards positive and negative infinity of our expression in its generalized form is 0. Well, 0 is unsigned, so that actually doesn't help us with any of the signs, and so we need to have an alternative approach to doing this. And the best way, I would say, is find an interval that has a simple or easy number to plug in. In our case, 0 is right here in this interval. I'm going to put in 0, and we're going to get 1 in the numerator, negative 3 in the denominator. 1 divided by negative 3 is a negative interval. So by starting out with that negative interval, that's going to help us find all the other intervals. This 0 has a multiplicity that's odd, and each of these values for x have a multiplicity that is odd. And so that tells us that the signs will change on either side of all these values on our sign chart. So if we start with the negative interval here that we already came up with, that must mean this is a positive interval, this is a positive interval, and it alternates. This must be a negative interval. The end behavior can be 0 and have a signed interval because our horizontal asymptote, if we were to analyze this graph, this will have a horizontal asymptote of y equals 0. And the signs actually tell us that if we were to graph this function, the negative here in the left end behavior tells us that the graph will be approaching the asymptote of y equals 0 from below the x-axis. It will be approaching sort of like this, if here's your asymptote. And the positive interval on the right side tells us that we'll be approaching 0 from above the x-axis, so that the values are positive. So that's how you can have end behavior of 0 and yet still have signed intervals. So lastly, we've got our sign chart, we've got the signs, we've got our zeros, we've got our undefined values. We look at the inequality to determine where is this expression less than or equal to 0. Well, here's the less than part, here's the less than part, and there's only one equal to part, and that's the negative 1/2. So our final answer is the interval from negative infinity to negative 3, not including negative 3 because that makes the expression undefined, union the interval from negative 1/2 to positive 1, again not including positive 1 because it makes the expression undefined. And there's your final answer for that inequality. One last example here of a rational inequality, and this is a little bit different than the previous two examples because we see two rational expressions, one being subtracted from the other. And when we see that, we remember that we've got to get common denominators to combine these two rational expressions to solve the inequality less than 0. So that's going to be our first priority, is to combine these two expressions into one big rational expression. So that means we need to find the least common denominator. It's going to be the product of the first denominator and the second denominator. That means 3 over x minus 1 needs to be converted to the least common denominator of x times x minus 1. We're going to accomplish that by multiplying both the top and the bottom by x. And that gives us 3x in our numerator. We've also got to convert 1 over x to have the common denominator. And that's going to require multiplying top and bottom by x minus 1. And that multiplication is fairly simple, x minus 1 in the numerator. So now our subtraction looks like 3x over the common denominator minus x minus 1 over the common denominator. Remembering that this subtraction we need to apply both to the x and to the minus 1. And that's going to give us a final combined fraction that looks like 3x minus x is 2x minus negative 1 looks like plus 1. And all of that is over the common denominator of x times x minus 1. And it's best to leave that factored already because we're going to try to solve for what values of x make this expression undefined, like we've been doing. And so that inequality is now less than 0. So now solving for the zeros for our sign chart, zeros, we want the numerator equal to 0. We'll find that that's negative 1/2. And we'll solve for the values that make this expression undefined. That's the denominator equal to 0. And that is, those are the values x equals 0 and the values x equals 1. Again, we're going to find that our end behavior with the 2x in the numerator and the x squared in the denominator, the end behavior is going to equal 0, which doesn't help our case for finding the signs on the sign chart. But we've got three values again. We've got x equals negative 1/2. That was a 0. We've got x equals 0, causes the expression to be undefined. We've got x equals 1, which also causes the expression to be undefined. And here's a case where our end behavior doesn't give us a clue to the outside interval signs, and we have x equals 0 on our sign chart, so we can't pick x equals 0 as a potential value to plug in. So instead, we can pick something else that we're comfortable plugging in, like let's say x equals 2. X equals 2 is right here on our sign chart, somewhere over in this interval. So if we plug in x equals 2, we get a positive numerator divided by a positive denominator, and that gives us a positive interval on the outside. Again, each of the multiplicities of the values that cause the expression to be undefined and the value that causes the expression to equal 0, each of these multiplicities is odd, so the signs will alternate, positive to negative, positive to negative. We're going to solve our inequality here. Now that we've combined the original expression, we want to concentrate on this inequality here, the less than 0 part. We want the negative intervals, and that's it. We don't even want the actual endpoint. So our final answer, the interval from negative infinity to negative 1/2, not including, and union, the interval from 0 to 1. Definitely not including those endpoints because they would make our expression undefined. And that's the solution, both with combining the two original fractions and then using the sign chart to solve.